Thank you for a nice introduction. My name is Hossein Tabatabaee, and here is our work on deficit round robin. Deficit round robin, or a DRR, is a simple widespread packet scheduler. With DRR, we have several queues or clients, and we want to share a resource or a bandwidth among them. For example, here, I assume that we have 3 flows, 3 queues, and I want to run a DRR to serve these packets of them. For the first queue, for the blue queue, I assume that I have 3 packets with the following sizes. So what a DRR does is first allocate some quantum value to each queue. Here, I allocated the same quantum equal to 199 bytes. Then it will visit this queue in a round robin manner. When a queue is visited and the queue is not empty, the value of the deficit of that queue is increased by the value of the quantum. Then you could send several packets, and the value of the deficit is decreased with respect to the size of the packets that were served. And whenever the deficit becomes smaller than the size of the head of the line packets, the service for this flow stops. And this is what we call a residual deficit, a deficit that is kept and can be used in the following rounds. For the second queue is the same thing. We increase the value of the deficit by the value of the quantum. We will serve some packets and decrease the deficit. What is special here is that we reach what we call the maximum residual deficit, which is simply the maximum packet size of that flow, of that queue, minus 1 byte. So if everything was in bit, we replace this like 1 bit. Here, assuming that the maximum packet size is 100, the maximum residual deficit of that flow is 99. We'll do the same thing for the last queue. And as you observe, the queue becomes empty. We served all the packets. In such cases, we set back the deficit to 0. This is one complete round of DRR, and the server repeats the same algorithm to serve the remaining packets. DRR is very simple, and it achieves fairness in the presence of variable packet lengths. And today we are interested to find delay bounds on the worst cases with DRR. Bounds on the worst cases were found by Boyer et al., where they found a strict service curve for DRR. Having a strict service curve beta means that in any backlog period of duration tau, at least beta of tau, beta of the duration of the backlog period, bits is served for that flow. But why do we care about strict service curves? Because they provide proven delay bounds, and here I explain how. If for a flow, we know an arrival curve alpha, as well as a strict service curve beta, then we could find a valid delay bound by finding the horizontal deviation between these two curves, the longest horizontal line that we could draw between these two curves. So what Boyer et al. Did, they assume a DRR server where for each flow we know the allocated quantum as well as the maximum residual deficit. Also, they assume that we have an aggregate, we have a strict service curve offered to the aggregate of the flows, a strict service curve for the DRR subsystem itself. And then here it is, the strict service curve of Boyer et al., which is in fact a rate latency strict service curve with the following rate and latency. Delay bounds of Boyer et al. Dominates all previous works when there is no assumptions on the interfering traffic. Having no assumptions on interfering traffic on one hand means that these delay bounds are valid even when the interfering traffic behaves in an unpredictable way. On the other hand, these delay bounds might be very pessimistic when interfering traffic behaves as expected and or actually constrained. For such cases, Sony et al. Provides a correction term to the delay bounds of Boyer et al. These correction terms takes into account the arrival curve constraints of the interfering traffic and significantly improves the bounds found by Boyer et al. However, this correction term is based on some plausible arguments that are not formally proven. And unfortunately, our first contribution is that we show that the delay bounds of Sony et al. Are incorrect. We show this by exhibiting a counter example, which is a single DRR server with 3 queues. In this example, we found an execution trace. We found a trajectory scenario where the delay experienced by a packet is strictly larger than the delay bound found by Sony et al., which is in contradiction to the bound being a delay bound. Very recently, Sony et al. Has revisited the method, and they make their delay bounds a bit larger, so hopefully now it's correct. We also found a convex strict service curve for DRR, but this strict service curve takes into account the arrival curve information. For one example here, I assume some arrival curves for the flows, and here I'm plotting the curve found by Bouillard as a comparison. I'm plotting the strict service curve of Boyer et al. Then if we plot the arrival curve of the flow of interest, we could compute the delay bounds. And as you observe, take into account the arrival curve information improves on delay bounds. This bound is formally proven, and the method works only for concave arrival curves. So here is a summary of the state-of-the-art on delay bounds on DRR. With no assumptions on the interferring traffic, we have bounds of Boyer et al. With the knowledge of interferring traffic, we have Bouillard's bound. And our next contribution is basically to improve both. Well, back to the original problem, where there is no assumptions on the interferring traffic, the same assumptions as Boyer et al. Here as novel strict service curve for DRR. This is a strict service curve that improves on delay bounds of Boyer et al. To obtain this strict service curve, what we did was to write all constraints without any attempt to approximate them or invert them at multiple at the intermediate point, and only at the end we use lower pseudo-inverse technique to invert them. This contrasts previous works where, for a tractability reason, approximations needed to be made at multiple inversion points. At the end, what you obtain is a closed form formula that we know is complicated, and we're going to address it, but let me illustrate it. Here in this example, I have plotted our novel strict service curve for DRR, which is a non-convex strict service curve. We show that it is tight, meaning that it is the largest strict service curve for DRR, of course, with no assumptions on the interferring traffic. Then if we know an arrival curve for the flow of interest, we could then compute a delay bound. Since it's non-convex, might be complicated to use in the tools that we have now. In fact, any lower bound to our strict service curve, any lower bound to this blue curve is a valid strict service curve, and can be used to derive valid delay bounds, but the result would be less good. Being interested in rate latency strict service curve, as they are very tractable and easy to use, we have found two rate latency strict service curve for DRR, well, the red curve, the one that achieves the maximum rate, and the green curve, the one that achieves the minimum latency. These two curves are non-dominated, meaning that there is no other rate latency that dominate these two. We can find a better strict service curve by taking the maximum of these two rate latency strict service curve, which happens to be the convex closure of our non-convex strict service curve. It's the largest convex function that lower bounds are non-convex curve. All these curves are very tractable, very easy to use. Interestingly, our rate latency with the maximum rate, the red curve, is exactly equal to the strict service curve found by Boyer et al. And that means that we are guaranteed to improve on the bounds of Boyer et al. We are as good as the bounds found by Boyer et al. Well, with no assumptions on the interferring traffic, we are as good as Boyer et al. So we are the best proven ones. Now let's go through the other problem, where the interfering traffic behaves as expected and specifically satisfies some arrival curve constraint. For such cases, we obtain a procedure, a mapping, to refine a strict service curve using the arrival curves of the interfering traffic. Specifically, if I know a collection of a strict service curve for all flows, as well as a correction of arrival curves for all flows, I have a mapping, I have a procedure that computes a better strict service curve for every flow. And how do we apply that? Well, I will start with our strict service curve that has no assumptions on the interfering traffic, the one that I just presented. I use the arrival curve information of all flows and will apply our mapping once. By doing that, I will obtain a better strict service curve for every flow. Here for flow I will obtain the red curve, a much better strict service curve. Now that I have a collection of better strict service curve for all flows, I can yet again apply our mapping. By doing that, I again obtain a better strict service curve for every flow. For flow I will obtain the yellow curve. In this example, in the second iteration, the service curve of all flows becomes stationary. So what we obtain is a procedure that we could start from our strict service curve with no assumptions on data frame traffic, iteratively apply that, takes into account the arrival curves of interfering traffic, and obtain an increasing sequence of valid strict service curves. So all these curves are valid, so we could stop iterating with respect to our computation budget. Here is the detailed explanation of our mapping, having a collection of a strict service curve, collection of arrival curves. We have a mapping defined here, which provides better collection of service curves. Key ideas to obtain this mapping was two things. So in our proof, we upper bound the service received by the interfering traffic using two analyses. One is our detailed analysis of DRR, is same as before. And the other one, we use the output arrival curve of the interfering traffic to upper bound the service received by them. By doing that, we obtain this mapping. Since we have an increasing sequence of valid strict service curve, we can obtain a decreasing sequence of valid delay bounds. Again, all these delay bounds are valid. However, in the tools that we have, working with non-convex curves and using nonlinear operations might be costly. Well, in order to address that, we obtain simpler version of our scheme by two things. So we start from our convex strict service curve rather than non-convex ones. Moreover, we replace the nonlinear part of our mapping with a convex expression. By doing that, we will obtain convex service curve that are easy to compute. Here, and for the same flow as before, in the right figure, I'm plotting the strict service curve that we obtain using our main scheme, the one that we just observed. In the left figure, I'm showing the strict service curve that we could obtain from convex versions of our scheme. As you observe, they are continuous and convex and easily to compute. Again, every curve that you see here is a valid service curve. Another feature of our method is that we could improve on any already available strict service curve, which means we always could improve on Bouillard strict service curve. We can do even better. So let's see what is the best strict service curve that we could compute as the initial service curve for our procedure. So on one hand, we know we could compute our non-convex strict service curve with no assumption on the interfering traffic. We could also compute the Bouillard's strict service curve. Since these two are non-dominated, we could take the max of two. Since the maximum of two strict service curve is a valid strict service curve, then we could use these curves and apply our mapping. If you insist on using convex curve, well, we could do the same thing. We could compute our convex strict service curve with no assumption on interfering traffic. We could compute Bouillard strict service curve, take the max of two that remains convex, then apply our mapping one again. Does it matter if you use Bouillard strict service curve? Although practically no. In examples that we tested, using Bouillard's strict service curve as an initial curve does not improve the bounds, meaning that the final curve that we obtain is exactly the same as the one that I showed you previously without taking into account the Bouillard strict service curve. So with or without assumption on the interfering traffic, we have fine proven bounds that dominates the state of the art. Now we could go through some numerical evaluation. Well, we use the industrial size network that was used by Sony et al. We have 8 switches, more than 6,000 flows with 3 DRR classes. Here, paths are chosen at random, but remains feed-forward. We use total flow analysis, TFA, as a network analysis. And here I'm plotting the delay bounds that we obtain for every flow. The top curve is the delay bound of Boer et al. Then the flows are ordered by these values. The first observation is that our bounds, as expected, improves on the delay bounds of Boer et al. Also, in practice, we are even better than the incorrect bounds of Sony et al. Note that the revisited bounds of Sony et al. Would be something larger than the incorrect ones. When comparing our bounds to Bouillard, we see again that we have an improvement. But the part that I'm interested is for these flows. So here I plotted the zoomed version of delay bounds of flows with the lowest delay bounds. As you see, when the delay bounds are very small, we have a significant improvement. We have a considerable improvement. And that is thanks to our non-convex strict service curve. The takeaway message here is when we use non-convex strict service curve and when the delay are very small, that could bring a considerable improvement. Well, I said that we chose a path to be feed forward. You might ask, what is the problem with networks with cyclic dependencies? When applying combining TFA and DRS6 service curve with network with cyclic dependencies, we observe that there is a two-way dependency between our DRS6 service curve and TFA. Because in order to compute our DRS6 service curve at a node, we need to know the arrival curves of the interfering traffic at that node. We could compute such arrival curves by applying a TFA. However, TFA needs to know the service curve in advance. When the network is feed-forward, it's not a problem. We could start from edges where we know all the arrival curves and go one step at a time deeper in the network. But with cyclic dependencies, we have a loop. That makes sense to propose iterative method, a fixed point method. And that is what we did in our newest archive method. Let's call it TFA-DRR. We obtain a fixed point method where obtained bounds at each iteration are valid bounds. So it's a refinement procedure. So here on the same network as before, but now paths are chosen at random. So we have cyclic dependencies. Here I'm showing the bounds that we obtain at the different iterations of our method for all flows. So as you see in the first iteration, we have bounds that are valid, but less good than the second iteration. In this example, applying the method in the second iteration, the delay bounds of every flow becomes converged. That's very good, but not perfect. So we use a TFA, but TFA known to be dominated by the polynomial sized linear program of Bouillard. It's a PLP with other PLP. And that's what we did next. We proposed a method called PLP-DRR, which we combine PLP and our DRS6 service curve. So what do we gain when we do that? Well, I try to illustrate it here. On the same example, I applied our mapping. I apply our method with TFA and once with PLP. As you see, there are two things. So first of all, there is a significant improvement compared to TFA. Second of all, we also obtain a larger stability region. For these flows, TFA gives infinite bounds. Note that the maximum lake utilization is also high. However, thanks to PLP-DRR, we could obtain finite and reasonable bounds for all flows. So I invite you to read our latest article. And that's it, and thank you very much. Thank you, Hossein, for the lucid talk. I think we have plenty of time for questions. Yeah,
a quick question and a long question. A quick question was on slide 20. Do you treat the curves? I mean, so when you have this multi-node analysis, do you treat the service curves still as strict or?
As strict service curve.
They're still strict, so you combine strict.
We use.
Still get strict service curve.
Can you repeat the question?
Well, the question is, Do we use a strict service curve for the network analysis?
That's correct. I mean, each component
Mhm.
is strict, but if you make a network to combine them, there's no convolution.
No, there is no convolution. So we are using TFA. So when we visit a node, we will compute a delay bound and propagate the rival curves.
Nice. Thank you. The other question that I have was, since you have a best possible strict service curve for DRR,
Mhm.
if you compare it to the best possible strict service curve for GPS,
Mhm.
you get the deviation between the two. And I don't think that people know about that, but you could provide this. Have you done that?
No, we've never tried that.
I would, if you do this, I would like to see that plot.
Yeah.
Because that is, to my knowledge, not known what the deviation is. Because this would then be, in my view, the worst kind of bound of the deviation of the service provided by the.
So I've never done it, but thank you for informing us. So we'll try.
Right. There's another question. You consider that we're implementing also cyclic dependencies.
Yes.
If there is a cyclic dependency, then how do you know that this is a starting point or defined on key programs? And is there any starting point when cyclic dependency?
So you mean here?
Yes. I mean, when you consider the cyclic dependencies, do you know where to start from? The starting point.
Well, the question is when we have cyclic dependencies, how do we find a starting point for this fixed point? So to answer that, for TFA, there are different methods of TFA that will be discussed by Stefan. But for that, we could start from, for example, 0, and at the end, when you reach the fixed point, you reach a valid delay bounds. In our method, is a little bit different. So when in our TFA DRR, we start from valid bounds. So if your question is regarding TFA, with TFA, we start, for example, putting the burstiness everywhere equal to 0, and we start iterating from there. And there is a proof that at the end, when we reach the fixed point, it is a valid bound.
Other questions online? No. Okay. I have one quick one. I think it's like 14 or something about this iterative method. No, yeah. Yes. So no, going back. Sorry.
So I will go back. I guess this.
Yes, this one. I get how you go from the blue line to the red line, but what is the intuition that another iteration improves, the second iteration improves the
yeah. So I could use this formula. Yeah. So the question is, well, I guess in our method, why obtaining a better strict service curve will improve than obtaining a
from 1 to 2 and
yeah.
so on. Yes.
Yeah. Yes. So I could explain it here. So as I said, we upper bound the service received by interfering traffic using the output arrival curve of that. To compute the output arrival curve, we are using the mean plus the convolution, which we use a strict service curve that we have, the collection of strict service curve that is available. So if you improve the collection of a strict service curve that you have right now, you could improve the collection of strict service curve that you could find. Yeah.
Okay, so let's thank Hossein again. Two more questions.
So is there an asymptote here that you basically, because if you keep doing this, you will reach like a point where you get to an asymptotic value?
So the question is whether we are guaranteed to converge at some point.
Yeah.
Yes. So.
Some characterization of that rather than computing.
Well, the question is, I guess, whether there is a guarantee that we will converge. So we have a simple convergence. So since we have an increasing sequence of curves in a finite compact, we will converge at some point, but we do not necessarily need to converge. as we obtain bounds, valid bounds at each iteration.
Thanks again, and